For this lesson, we're going to start talking about the next part of the rotational linear comparison. We're going to look at rotational work and energy. Rotational work and energy, we can kind of understand how rotational work and energy work by first looking at what we know already. Let's talk about linear work. We know linear work is the dot product of the force and the displacement. S is, instead of X, we use S because S is used to represent 2D displacement or 3D displacement because it takes into account the X, the Y, and the Z. Alright, so if we have, for example, this wheel here and it's being pulled by a certain force, the certain force is going to cause some kind of rotation in the wheel. If we wanted to calculate that the work done by this force, we can use the linear formula that since the force and the displacement of the rope or the direction is parallel to each other, we can simply write that the work is equal to the force times the magnitude of the force times the magnitude of the displacement. And since this is just one dimension, since the force and the displacement are both acting on the x, we can just say the work is equal to force times whatever the displacement in the x is. We can start changing this into a circular motion type equation by understanding that the displacement in the x is equal to the angular displacement times the radius. So when we combine these equations, we have work is equal to the force times the angular displacement times the radius. From there, we can go and figure out that since we're multiplying the force and the radius together, or how far away it is, that's the formula for torque. So we can rewrite the equation as work, rotational, work circular, work angular, whatever you want to call it, is equal to the torque times the angular displacement. If torque is constant, meaning the force that's causing rotation is constant, then we can just use that equation. If not, we're going to have to use some calculus, and the calculus would simply be that the work is equal to the integral of however the torque might be changing with respect to the angular displacement involved. So if they give you the formula for angular displacement they give you the formula for torque with respect to the angular displacement, the integral of that would give you the work done. For kinetic energy, we can kind of solve it the same way. We start off by, if we look at this, we have a wheel that is rotating. Because it's rotating, each particle away on the wheel has a certain tangential velocity. So pretty much the kinetic energy of each particle, well, each particle also has a mass. So each particle is going to have a kinetic energy. It has the two stipulations. It has both mass and velocity. So the linear kinetic energy of the equation would just be the kinetic energy of each particle is equal to 1/2 the mass times Vt squared. And since tangential velocity is equal to the angular velocity times the radius, we can find the kinetic energy, angular or circular or rotational, whatever you're going to call it, is equal to 1/2 the mass times the angular rotation times r, and all that squared. If we break this up or distribute the angular velocity times r squared, we get 1/2 mass times radius squared times angular velocity squared. If we remember the formula, what happens when we take the mass and multiply times the radius square of an object, we actually get the inertia. So, and since the sum, all the kinetic energy of all the particles is equal to the sum of the kinetic energy of everything. So the kinetic, now for the most part, 1/2 is a constant. The angular velocity of every particle in this rotating mass is constant. Right? That's one of the definitions of a rigid body, assuming it's a rigid body. And the 1/2 is constant, so we can kind of remove it out of the equation. The total kinetic energy is 1/2 the angular velocity squared times the total sum of the masses times the radius squared of each particle, which is also the formula for inertia. So we get kinetic energy, angular, circular, rotational, whatever you want to call it, is equal to 1/2 the moment of inertia times the angular velocity squared, which is the same thing as the sum of the mass of every point times the tangential velocity of every point squared. So that gives us our kinetic energy equation for objects that are rotating. So, mechanical energy equation. Linear mechanical energy equation simply says that the mechanical energy is equal to the total kinetic energy plus the total potential energy. This is so true, but since we technically have a translational kinetic energy, which is 1/2 the mass times velocity squared, plus rotational kinetic energy, which is 1/2 the mass times the tangent velocity squared, or simply 1/2 the moment of inertia times the angular velocity squared, that will give us the total kinetic energy. And when we add it to the potential energy, we get the total mechanical energy. So we just took the same mechanical energy and extended. Before mechanical energy equation, we said mechanical energy was equal to 1/2 mv squared plus mgh. That was technically true at the time because we didn't deal with objects rotating, so the angular velocity was 0, so there was no rotational kinetic energy. But when things rotate, there's rotational kinetic energy, and we have to take it into account. So kind of recapping everything we have our equations and their equivalents. We have linear displacement, angular displacement, linear velocity, angular velocity, linear acceleration, angular acceleration. We have mass, which is a measure of inertia. We have moment of inertia, which is measured in kilograms, meters, kilograms meters squared. We had center of mass for linear, we have center of gravity for angular, we have net force for linear, we have net force for torque, and we know since net force is equal to mass times acceleration, we can just replace everything, so that means net torque is equal to moment of inertia times angular acceleration. Since work is equal to force times displacement, or the dot product of it, work angular or circular can be considered torque times angular displacement. And then last we have our kinetic energy. And the only thing left to discuss, which we will do next class, is momentum. And then we're pretty much complete. We just need to cover the last one, comparing linear momentum to angular momentum. That's it.